Welcome and hello to everyone who joined today for the Altair webinar series for students. We are excited that you're here and excited to give you some outlook on how to get started or how to start with simulation disciplines. Today with me is my colleague Joyce and my colleague Laura Joyce is from the UK office and Laura from our Spanish office of Altair. My name is Jan, and I work at Altair Germany as the account manager for academics. So my job at Altair currently is talking to professors, to students in the mid-European region of Altair. Before that, I worked as a project engineer in Switzerland, and before that, I once was already at Altair as an software application engineer. My background is mechanical engineering, so I have a bachelor degree in mechanical engineering from the University of Cooperative Education, it's called, in Stuttgart, and a master degree in business and engineering from Steinbeis University in Berlin. So I'm happy to present you some things about how you can use Altair simulation software, hopefully in your projects, in your studies. All of these examples and demos and presentations that we give here will be uploaded later, so you can use them to reproduce the steps and reproduce the models later on using our free student version, but I'll talk about that in a minute. So what to expect today from the GoTo webinar. You're all in listen-only mode. So you will be able to listen and follow the presentations and demos. You will see basically my screen. Hopefully you do now. And you can use the questions tab in the GoTo window to post your questions to us, and we'll try to answer them either in written format or directly live after each presentation. As mentioned, the demo recordings and model files will be made available after the webinar, so you don't need to basically click in the software now, but we'll upload the model files and the recordings so that you can reproduce the demos later on your computer. All right. The idea of why we are doing this is basically we have gotten feedback in the last couple of years from student teams, but also from student projects, from professors, that software really helped them in their projects. For example, here's a citation from the German team of WHZ Racing, who basically did simulations with our software SimSolid, which is part of the demos today. And SimSolid is meant to do rapid and very quick simulations so that you will have a result within a couple of minutes or seconds, which will save you loads of time in the beginning of your project. So you can evaluate different CAD models, load the CAD model, perform simulation, and then hopefully will have the same success as WHZ Racing, that you can save a lot of time in the beginning by using this SimSolid approach. Another topic that will be addressed tomorrow is, for example, optimization with Altair Inspire. So using Altair Inspire, you basically can design in an easier to use workflow your parts for 3D printing or also for other manufacturing, for example, for small parts, but also for larger structures, where you will get a very high weight saving while using this optimization approach during your design and engineering process. So that really also will give you a head start and a good, basically a good time saving in your development process. So if you want to basically then use the student version and some further material and also access the demo recordings, you can go to our website, altairuniversity.com. So there you can access the free student version. You can download and install almost any of our software programs for free with a license file that's valid for 1 year. So if you go to altairuniversity.com, go to the student edition section, download or request the version and then download it, and you will receive a license file for 1 year, which is free of charge. You can also, if you're a student team, request a sponsorship license. So you can enter your data, for example, for the whatever Bacher team of your university, or formerly a student or Shell Echo team of your university. And we'll also provide a license file free of charge for you and your team. Now, if you want to educate yourself further, there's lots and lots of material available. For example, free ebooks on how to use SimSolid, how to use Altair Inspire, how to use any of our software programs. So just visit the altairuniversity.com and you'll find lots of material there to further educate yourself and also your student colleagues. All right, now I talked about the free student version, and what you will get is basically a license file with which you can access any of our software programs, right? So you'll get a license that includes Altair, any Altair program as a free student version. If you go through the campus license or through a sponsoring package, then you will even have more programs available. For example, you will have the full package without any limitation on model size or any limitations on like import or export filters. So if you have access on the campus, or if you want to have access for your team, go to altairuniversity.com and request a sponsorship. If you don't need the full version, the student edition would also give you access to basically simulation for electric drive design, for mechanical design, for fluid design, thermal and fatigue simulations, also control systems, and lots of other disciplines. So with one license file, you can do so many different disciplines and also combine those different disciplines. So do, for example, multi-physics approaches by simulating an electric drive, using the thermal load that will exist in the drive to map it on your structure, then map that to a fluid code to simulate the cooling. So you can combine those different disciplines also together, and it's all accessible within one single Altair license. So that's a big differentiator for us from the competition, that you don't really have to request each package separately. You will have one license and then you can download and use everything that we got. Okay, so for example, here's one short animation where different disciplines have been put together. Like look at this electric scooter or Segway. So one simulation that's been performed here is the dynamic system simulation. So basically moving this scooter around on a certain track. Then the whole system, the dynamic system, needs to be controlled so that it doesn't fall over. So there's a control system, a control mechanism included, which will hold the scooter upright to basically follow the dynamic route here. You have to engage two engines, two electric drives. So those are seen in the left and right lower corner, where you will see the electromagnetic field and the thermal load that will happen during the motor movements. So while the scooter is moving, the electric drives are simulated as well. And the thermal load can be then mapped, for example, to the structure. And finally, there's a structural simulation. So at the end of the video, we will see that the platform has been structurally optimized to carry the load of the person that stands on the scooter. And yeah, then again, you will see that we have created a rendering of the whole simulation, right? So the whole video also has been designed and then rendered in our CAD software. So that's just an example of how to combine different disciplines together within the Altair license system. So one question is, if you want to start using simulation, why use it and when to use it? And So from experience that I have as a project engineer, but also from many, many customers and also from student projects, what we saw and still see is that many projects will start with the first CAD draft in the early design phase. So over the time, you basically will see that you first have a CAD model, then you create a simulation model from that CAD, start your simulation, and give back the results after some time to the CAD guy or to the CAD system. And what might happen is that during your simulation, there have been changes in the CAD model. During your simulation, there have been changes maybe in another department or from another influence. And now your simulation results don't match the CAD data. So that's a problem, because now you have to reiterate, you have to recreate a simulation model, you have to do different design loops, and that will basically prevent you from getting the highest performance or getting the highest knowledge out of your simulation. So our suggestion is to use optimization and simulation at the very beginning of your design stage. So not start with the CAD model, but start with simple simulations, start also with optimization simulations, perform different studies at a very early stage of your design, even if you don't have a full CAD model yet. And that will enable you to reach a higher maturity in your design at a very early stage. And basically it will enable you to gain performance of your design and save you some time by saving the design iterations between simulation and CAD design. So that's what we would suggest, to use simulation as early in the design process as possible. All right, now let's get started with the first track for today. We'll have 2 additional getting started tracks tomorrow and on Friday. Today we are mainly focused on first an introduction from our panelist Simon, who will give an introduction to simulation results from his student team experience that he had in the previous years. Followed then by a demo and presentation of Joyce, who will talk about kinematic and dynamic system simulation with the program Altair Inspire Motion. And then Joyce again will show you and demo a simulation with Altair SimSolid for fast concept evaluation. So that's the agenda for today. More topics are to follow, as mentioned, tomorrow and on Friday for the Getting Started track. We'll have 2 additional tracks, Advanced Simulation and Data-Driven Simulation, which will happen next week and then the week after. All right. I see there are a few questions, so let me just check those. One question was, is it possible to renew the student license after it expires? Yeah, that's possible. So you can renew the student license after 1 year if you are still enlisted in the university. All right, so the first panelist today is Simon Hillebrand of Ecury X Racing in Germany. So Simon is a student of industrial engineering in the 6th semester. He has participated and reached a national competition at a national research competition, Jugendforst in Germany. And since 2019, he works with the student team Ecury X in Aachen, Germany, being the group leader for frame and composites until recently 2021. He had that position. So Simon will give you an introduction on simulation of a bit more advanced topics. So it's not really how to get started with simulation. It's a bit more how to use it for composites, for aerodynamics, for lightweight optimization. So the topics that he's talking about will then be addressed in the advanced simulation track happening next week. So, but I think it will be a good thing to have an outlook on what's possible with using advanced simulation techniques as well. And so I'll ask Simon to start his presentation now.
Hello and welcome to my presentation at this Altair workshop, and many thanks for your interest into my or to our work. My name is Simon Hillebrand and I'm a part of the former student team EQRX from the RWTH Aachen, and I'm the former group leader of the chassis group in our team. Today I can present you some impressions of our work we have done in the past year related to the Altair software. A short overview: what is Formula Student? Formula Student is the largest student design competition in the world and founded in the USA. Currently we have over 600 teams from universities and college all over the world. And they're built and they construct and build every year a new one-seater race car, as you can see on the picture on the right side. And then competitive in several disciplines against the other universities. Then there's the Formula Student Germany, the FSG. It's the biggest event in Europe. Nearly 70 teams take part in different classes. And there's there's 1 week in Hockenheim where the races take place, and also the FSG writes our regulations for the season. To get a short overview what I'm talking about, in the beginning I want to introduce you into our team. Then I give you an overview about our last season and about the success we got. And then I want to talk about the Altair software we use. And in the end, I will give you an overview about the highlights in our current cars, which are related to the use of the Altair software. Especially the chassis or topology optimization and the structural aerodynamics simulation. Here you can see the team from the season 2020-2021. EQRX is founded in 1999, and which makes up the second oldest Formula student team in Germany. And currently we have over 80 active members and over 400 alumni. And in the history of the club, we already built 10 combustion cars and 9 electric cars. In the front, on the right side, you can see Nuri, our 9th and most recent car. And on the left side, you can see Rita, the 7th electric car in the series, and which we have converted into a driverless car to take part in the competitions for the driverless cars. Here's a short overview about our team structure. We have the club board and 3 technical team leaders. The mechanical team leader and the electrical, and the third one is the administrative team leader. And then we are subdivided in 8 sub-teams, which operated underneath these team leaders. And so this way we can be sure that each department can specialize in its field and get the optimal performance out of this season. And the frame and the aerodynamics are the 2 groups which work mostly with the Altair software. There are some groups which work partly with it, but we are the groups which work the most time with the software. It makes our work a lot easier, and so we can achieve much better results. As I said, we are founded in 1999, and in 2002 we had our first drove with our first combustion car, the EAC01. And then in 2010 we built our first electrical powered car and run the two classes parallel until 2013, where we built our last combustion car. And in 2017, we added the driverless software and sensors, cameras, all you need for driverless car onto our 7th electric car to start competing in the driverless class, as I said. Here you can see the EIC09, the car where we take which one will take part in the events in this summer, the last month. It weighs 165 kilograms, has a full aerodynamic package, which means front wing, rear wing, under tray. Is a 4-wheel driven car, and the focus is completely on lightweight design to gain the optimal performance. On this slide you can see the EIC is 07.D. Point D stands for driverless car. It's called Rita, as I said, and weighs 220 kilograms. And is driving with a LiDAR and 3 cameras, which we added on the top of the car on the main hoop. We also need a car PC with software, which we developed by ourselves. With this car we competed this summer. Also in Europe. Here are the results from the summer from the EV car. It was a really successful one for our team because we won the first time a competition overall in club history, the Formula Student Austria. And also we were always close to the podium on almost the others as well. And we had a great success also with the driverless car. We were able there to achieve the 3rd place in overall in Hungary, so in Formula Student East. And that's the whole thing is based on a lot of work and development in the past years. Also with the software from Altair, which I will present later, especially because when we do lightweight design, because the weight of the cars plays a big role in Formula Student, we want to keep it as low as possible because it's a sensitive parameter when we think about a car which can competitive with the other teams from other universities. So we do not achieve the low weight only because of the choice of material, but also with new geometries, lighter geometries, optimized geometries. But there I have an example later. The software we use is on the one hand there's ESAComp, where we use it for, I will explain it later. Mostly we use HyperMesh with the Solver OptiStruct, where we do all structural simulation with. But also Altair Inspire is very exciting for us because we can rebuild our topology optimization with it very well. On the following slides, I would like to give you an overview and more detailed impressions of what we do with the software, what we have achieved with it and how our workflow looks like. Here, let's start with ESAComp. When we start to design a monocoque, we did the pre-Lamini design with ESAComp. We simulate there a 3-point bending test because it's prescribed by the regulations we got from the FSG. For some years now, we've been using a sandwich structure in the monocoque, which means that there are a carbon outer layer, a core material, and an inner carbon layer. And that gives a lot of structure So, and at the same point, a lightweight design. And so in ESAComp, we can iteratively change the layers or the core materials, for example, aluminum, honeycomb, or the angle of the layers we want to lay in the panel. And so we can click them fast together and simulate them also very fast. And then in the end, we can incorporate these results into the monocoque simulation, which you can see on this slide. Here you can see our current monocoque in Hypermesh. After we had constructing it finally, we removed all detailed parts which are too complex, so it simplified the meshing very well. And then we declared some different zones in Hypermesh so that we can improve them locally more easily, because then we can assign a whole ply to the whole zone more quickly. And then in addition, we simulate the whole monocoque on a ply-based simulation and instead of a zone-based simulation. That makes us has more freedom for our constructor in Hypermesh to play more around with some plies. Also, the main hoop and the front hoop are integrated into the simulation. They are simulated with an 1D beam element. With the corresponding material values from the steel we use for those two parts. We integrate them because they are main parts of the monocoque, and they are stable them also quite much. We also already we every time simulate our monocoque for torsional stiffness, which means that we fix the car on the back and torsion them in the front. We are doing this because when we have a good torsional stiffness, which we simulate in the beginning, how much we need, we can be sure that there's also sufficiently present a good bending stiffness, so that we can set our setup quite well. And in addition, the suspension rods are modeled with tubes with our own material values, and the wheel hubs are infinitely stiff parts, and we use RBE2 elements to simulate the connections between the monocoque and the hardpoint, as you can see on the left picture. And then we are able to apply a force on the front axle on the one side and fix the monocoque in the rear completely, except one side in the movement in lateral direction. The force in that direction isn't that important or relevant because we calculate the torsional stiffness later, linear elastic, and from this value we calculate our torsional stiffness. Here you can see simulation result from the monocoque simulation. You can see that the red part of the monocoque deviate a lot. Or that means that there the monocoque has the most torsion. So then we can measure the displacement from the point where the force acts and calculate then our torsional stiffness. And after many iterations and a lot of simulations, we achieved our goal and had in the end a torsional stiffness which was greater than 5,500 Newton meter per degree. And it was somewhat higher than our target, so we were happy with it and decided to build or laminate this monocoque in this season. Another example of another part in the car which we designed with Hypermesh is the steering cage. It's right behind the dashboard and stores our steering. And yeah, here we were able to save a lot of weight due to the fact that we used the topology optimization. Yeah, after we printed then out the result out of aluminum. And here on the slide, you can see the installation space we gave the program and the corresponding bearings with their forces and yeah, the forces which the simulation should take into account. And we determined these forces before, and so that we got a realistic simulations for our steering cage. And after a simulation, or after some simulation, we got this result. Yeah, it's always exciting to see those results from topology optimization, because you can learn a lot about the load paths from these different forces, and yeah, also for different materials when you tried it out. Yeah, it looks every time a little bit different. And so yeah, this was our result for the steering cage. And here you can see now where we began to reconstruct our result from the simulation. We did this in Altair Inspire, and yeah, tried to do it as closely as possible to the simulation result. It took a lot of time, but with the result, yeah, was quite nice. And after we constructed, finally, we go back to HyperMesh and simulate the constructed part with the assumed forces and the same connections as the topology optimization. So yeah, that we get then an idea of how the construction works, and maybe yeah, maybe we can save somewhere some material to save some more weight. So it was an iterative loop of simulation of a simulation of the result, and interpret then the results and remove some material and simulate them again until we have a final result where we could save 30% of weight compared to our old concept, which was a welded aluminum cage behind the dashboard. So yeah, quite a lot when we think about this small part. Here you can see the final printed result, including the built-in steering, as it is also installed in our current car. Yeah, and on the right side, you can see how the printed parts comes from the manufacturer, still having the support structure inside, which we have to remove and yeah, make some different things with it before we could install it into our car. Yeah, then I have another assembly group which were designed with HyperMesh, the aerodynamics. So we simulate all structural things for the aerodynamic HyperMesh. After we retrieve the geometries from the aerodynamics group, we can simulate the layup and the inner structure for those parts. We calculate on the one hand with the aerodynamic load, and on the other hand with the loads from the regulations. For example, every aerodynamic part is allowed only to displace 10 millimeters while acting 200 Newton on a surface of 225 square centimeters. And yeah, here you can see the whole rearing in the simulation, but also some individual flaps for some individual simulations to become a more precise result. Yeah, and with this concept, we simulate every aerodynamic flap and try to get them as stiff as possible with the lowest weight. before we start to manufacture them. And another example is the front ring. Here you can see the main element. Yeah, it includes a lot of points where the force acts. Yeah, we did this because we want to be sure that at every point the rules are or the part is fine with the rules. And here at the green part of the main element, the flap were completely fixed in all directions, as it is later in the monocoque. So that we had a realistic simulation as possible, so that we can be sure that the front wing we build then later is rules compliant too. So yeah, here you can see on the next slide the result from the simulation. It's a result from the force acting most outward. So yeah, it has there was the most displacement, obviously, because of the largest lever arm. And yeah, after every simulation, we can see if it makes sense to add some more layers of carbon, maybe some UD stripes to support the structure, and or some different inner structures. And yeah, in this way, we did many simulations for every part to get the best layup for our structures. But for us, there's not only the displacement interesting, also the composite failure of the layup, because when they had too much stress, then they got they fail, and that would be not that good, of course. And yeah, that's also something we have to take into account, that all our fibers are still working under the loads we have in our races. Here's also the example, the front wing main element on the top and on the bottom side. There are different places where the composite failure is bigger, and where you could think about to add some more plies, to have a bigger safety factor. And then this was my presentation about the work with the Altair software in our Formula student team. I hope you got a good insight into our work and enjoyed my presentation. I want to thank you for your attention, and I'm available for further questions under the contact details shown onto the slide. Feel free to contact me there. Also, many thanks to Mr. Grasmannsdorf to giving us the opportunity to make a presentation here and share our results with with some people who are interested into it. And yeah, I want to say goodbye, and I hope you have fun in the workshop.
So thank you, Simon. I'm looking for questions that were related at that presentation. Unfortunately, he's not online right now to answer them directly, but maybe I can help a bit. And then, of course, as mentioned, Simon is open for mails, so you can write him under the address shown in his video. I think one question was which failure criteria was used during the simulation of the composites. So I'm not sure which one he used directly, but there are different failure models included in the programs that he mentioned. So he mentioned ESAComp, which is a laminate pre-designed simulation, where we will have the Hill and Tsai-Wu and Puk and Kunze failure criteria, and the same failures can also be applied in an OptiStruct simulation. So basically defining your material values and then defining a failure criteria. You can then, for example, look for Tsai-Wu failure, and you can even program your own failure criteria. So if you have a strain value or a stress value, and your professor or whatever has his own failure criteria, you are able to program that and use it in HyperWorks as your own user-defined failure criteria. Let me see if there are more questions related to the presentation. When you simulate the aerodynamics, you fill the whole wing with foam. I have to be honest, I can't answer that, so I'll write a mail to Simon and provide the answer after the session, okay?
I think I can answer that very quickly, just off the fly.
Mm-hmm.
When you want to simulate any sort of aerodynamics, you're normally just looking for the flow profile that goes around your structure. So whether if it's filled or not, I don't think it matters, because you actually just need to see, if there's any sort of trapped vortices around those areas. Hence why it's very important to get the correct surfaces and make sure that your geometry is properly enclosed. So you can fill it with foam, you don't have to. All you need to do is just make sure you have the right exterior profile for it.
Exactly, so that's for the aerodynamics. The profile shape is important. If you want to then simulate the effect of the aerodynamic forces on the bending of your, for example, the bending of your wing, then you might need to include the foam, but that's then a structural analysis again. So that's basically mapping the aerodynamic results to the structure again.
Yeah, exactly. Yeah. So it all just depends on what results you want. Where you can.
Exactly. And if you want to do the structural analysis, then of course the foam would probably be useful.
Exactly. Yeah.
To have it in there. All right. There are more questions not directly related. I think, there was one question if the aero profile might get deformed. Yeah, that's what I just answered. If you want to see the deformation, then probably the foam will be needed. But if you want to see the pure aerodynamic effect, then you don't need the foam. All right. So thanks again to Simon for providing this presentation. I heard there were some audio issues. I hope it was better after some time, because I turned down the audio on my side. Sorry for that. I know the presentation had some audio issues, but I hope it worked for the majority. Okay, so next up is a topic of multi-body simulation. So there were already a lot of questions related to that. Can I simulate mechanic systems, or can I simulate robot systems? So all these have basically moving parts, and moving parts means you can apply multi-body system simulation. So that is basically setting up a model of your joints, springs, dampers, and bodies, then define a movement on that, or define some sort of external activation and or external drives, and then the whole system can be simulated, and you can extract your loads. You can extract the loads at your joints, at your springs, at your dampers, for example, to use it in a for example, kinematic or dynamic system. So here's a suspension design, for example, where this might be useful. There are other examples like robots, or here this quadcopter or drone, where you also have moving parts, and all those basically can be used in a program called Inspire Motion or Motion Solve. And I let Joyce introduce that. So Joyce is my colleague from the UK office. She graduated from Coventry University in 2019 with a first class degree. So yeah, she's a brilliant young colleague working at Altair since 2018 already. And yeah, we'll be happy to give you an introduction to Motion Solve and Inspire Motion. I mean, both programs basically are used for multi-body system dynamics, but I think it's part of the presentation as well on when to use which software. So let me hand over the presentation to Joyce and have fun with her presentation and demo.
Thank you, Jan. So let me show my screen. Okay, so hopefully everyone can see my screen and you can all hear me as well.
Yeah, I can hear you and see your screen.
Okay, perfect. Thank you. So hello everyone. Like Jan said, I am an application engineer at Altair UK. Jan is one of my colleagues from the German offices, and we both work together on looking at the academic side of Altair. Now, for this session, what I'll be taking you through is looking at Inspire Motion and understanding multi-body dynamics. So some of you may have already started doing some of this, but some of you might have never actually come across MBD before. So within my session, we're going to address what multi-body dynamics is. We're going to then also start talking about the software and seeing what kind of simulations you can make with it. And last but not least, we'll talk about the benefits in looking at MBD, and we can address any questions that you might have at the end as well. So like Jan said earlier on, a lot of times when you're looking at simulation work, you use it as like a final validation. You know, ages back when computing resources were very limited, you would only use FEA as a form to validate something, to make sure that, you know, your design is good enough before sending out to being made. And that was, you know, back in the 1980s, the 1990s, where we didn't have that much computing power. Now, the more computing power we had, what we realized is that we're going to start pushing for simulation-driven design. And what that means is that you take your designs and you put them through simulations from the very beginning, during its concept phases. So you know exactly that you're designing it to be as efficient and as effective as possible, so that it's always doing its job. It can be as lightweight, and you know that it's always performing to the best of its ability, to the way it's going to be used. And like, you know, some of you had already asked as well earlier, you know, how do we make sure that it's also manufacturable? How do we make sure that it's performing right? This is what we call the balancing act. So anything that you do create, you always have different manufacturing constraints that you can implement in Inspire to make sure that it is manufacturable. And there's also the structural analysis that you can then look at afterwards to understand its performance. So understanding its key performance indicators, where your main stresses are, how much it's deflecting by. And this is what we mean by, you know, analyzing, generating, and then simulating it as well. It's all part of this simulation-driven design balancing act. Now, within the world of CAE, there's lots of different disciplines, and there's lots of different sectors of it as well that you can look into. So where we start looking at MBD, this is where we start looking at multi-body dynamics. You also have finite element analysis in itself. And within finite element analysis, you can then start splitting into different sectors, like NVH. You can look at durability. We can also start looking at crash and impact analysis. We then need to consider within those crash scenarios about our occupant safety and pedestrian protection. And anything that we design, it's going to be useless if it's not going to be manufacturable. So we always need to make sure that we can then look into the manufacturing simulations as well. And all of these just basically come into context of the fact that this is CAE. It's something for us to use in our workflows for designing, and it gives us a base point. So usually with our workflows, you know, how do we simulate them? We can either replicate physical tests, but say if we don't replicate physical tests, we know exactly how it's going to be used in real life. So say if you're trying to model a computer mouse, you know exactly how it's being held, how it's being used, and that's what we can replicate in our simulations. But then there are times, like say if you're looking at a suspension system, you don't always know the loads that are acting on your parts, and you don't always know exactly if you've got the right motion assigned to it. Now that's when we start looking at, a multi-body dynamics, to then take through into linear static analysis, to then take through into optimization. What I also wanted to let you know is that, you're not just limited to the one area of engineering. With all of our tools, you can look into biomedical, you can look into commercial goods, and you can even look into the data side as well. So one of the things that we're looking at from multi-body to linear static analysis, on YouTube, last year I did do a video for suspension design, where you can start looking at generating your dynamic analysis. And from there, you know exactly the loads acting on your part. You can then take those loads to optimize it. And then you can also conduct a final strength validation on it to see if it would fail during its time in use. And if it doesn't fail during its time in use, you've done your job. So the workflow in where it is that we might want to bring MBD into it is at the very beginning. We then take those loads for structural analysis, and then we can optimize it. So why is that? Why do we want to look into multi-body dynamics? We want to understand different part assembly mechanisms. We want to comprehend our motion characteristics. So we want to see whether if that spring is actually performing adequately enough for the motion of our suspension design. We want to design it for its intended use. So we need to make sure that, where we have our packaging spaces, we don't start designing out of our boundaries. We want to make sure that each of our parts actually withstand the way it's being used. It's not going to fail on us. And the moment where we start looking at, spring damper systems as well, this is where we can link it up into Activate, and we can then simulate and understand the feedback loops and the response loops to understand whether if we need to put more damping, less damping, more stiffness, or less stiffness with it too. When we're conducting an MBD, we can see the generated loads on each component as well. And once you actually get those generated loads, you can then take it through for structural analysis. So without further ado, I'm going to ask Jan to start playing a video that you'll also be able to watch on YouTube later. I'll be taking you through a tutorial in how it is that you can start using contacts. But if you do want to look at a suspension design, also on YouTube. So with this one, this is just talking about the basics of Inspire Motion, and it'll take you through in how to set up a Geneva wheel for analysis. So I'll be taking you through Inspire Motion today. Inspire Motion is our multi-body dynamics tool built inside of our Inspire GUI. Now, the times in which you want to conduct a multi-body dynamics tool is when you want to look at an assembly of CAD, and you want to look at the reaction forces between them. So at the end of this video, what I should hopefully be able to convey to all of you guys is that we can start looking at implementing some motion between our CAD and seeing exactly how our mechanisms work with one another. And consequently, after this, we'll be able to see the forces generated on every aspect of our model, within our joints, and within our springs that we have modeled into it. You can see the magnitudes and the direction of everything. And once we then calculate all of those forces, we can take certain parts, implement an analysis on it, so that when we do load it up and we click on play, you'll see it takes every single frame within that motion study you did, and it can conduct an analysis on it. And you can see once it's loaded, it will then start to play the animation again, and you can see the displacement contours that occur on your part. We can change our contours to looking at stresses. So once we let this load to look at the stresses, we can now see the stresses that act upon our analysed part. So you can see all the forces and the torques that were generated out from the motion study is now applied onto this part itself. And if I were to slow down the speed of our animation a little bit, just to understand it better, we can also change our legends. So let's say if we want to look at anything above 1 megapascal. We can see how our stresses vary in our simulation like this. So we can see every time it pushes it through where the stresses are above 1. And we can go through this one again. Scale it up slightly faster. And we can see all of these stresses acting on our part, to the point where the moment it unravels itself, we can see all of the stresses leaving the component. So let me show you how you can set this up yourself also. Now let's start a fresh session of Inspire, shall we? Inside Inspire, once you have it installed, if we head into the View toolbar, you'll see we have a demo browser, and here you can actually access the CAD that we'll be using for today. So let's look at M07, the Geneva wheel. Just simply drag and drop it in, and you can see that we have all of the CAD we need here. So at this part, what we're going to do is now simply click on the different CAD parts, and you can see this live synchronization in that where I click in the GUI, it will show us exactly what it is at the side. So within this tutorial, what I'm going to be showing you is the fact that we'll be going across this toolbar at the top here. So just make sure that you're using this toolbar at the top, and to access it, you just need to be in the Inspire Motion tab. We'll go through in setting up the first things we need, such as a rigid group, the joints to dictate the motion between different parts. We'll add in some motors, actuators to dictate the motion. We can then also specify some contacts, gravity, because we're assuming that this part will be used on Earth, and then consequently after that I'll show you how you can analyze the motion and do all of the post-processing that you also need. So first things first, what we'll be looking at is using the ground tool, and we're going to specify exactly what's going to be staying still in this whole animation. So where it is that we want to ground it and where it is that we don't want it to fly off from. We'll come into that slightly later, because the first thing we're going to do is set up our rigid groups. Rigid groups are great to dictate exactly what parts are moving relative with another part. So we can specify that this ring here, this wheel, as well as this partition part in the middle, all moves as one, because we're just going to assume that that's one rigid entity. We're going to assume the same for this cam and this driver as well, and just click create. Once that's done, what we'll then do is click for some joints. Now, as we said before, joints are used to dictate the motion between your different parts. So you'll see that we have the pin that we have here. If you just simply click on these red faces, we can specify exactly what kind of motion we want to dictate between them. So let's say a hinge, and we'll also lock it for the time being. We can do the same for this area here. Let's click on it again and specify that there's a pin that holds this top knuckle with the rest of the driver. Now, consequently after that, what we can do is also specify exactly how this box will be moving with the guide, so the slider and the guide itself. We'll keep it as translational, as the two surfaces can only go across one another, and we'll leave it as active. Now, last but not least, what we'll also do is specify exactly a pin in the middle here, so where we'll be holding our wheel. You can change it from looking from all to single holes, and you'll see that it's detected it, and we'll put a grounded pin in it. So you'll see that we can ground this wheel in where it is using a grounded pin, and this takes us to also using the ground tool, and we can ground this guide here. So once that's done, what we'll then do is start looking at gravity. So let's specify gravity being in the negative Z direction, which is fine. And in Inspire, we have what we call the crawl, walk, run method. So let's start off simple to make sure we have everything moving relatively as we need it to be, and then we can add complexity as we go through it. So currently we've already dictated all of our joints. Let's just make sure that everything is in place as it should be by clicking on the solve button. And what we will find is that the wheel should stay where it is, the guide should stay where it is, however we should expect to see that the cam and the driver to fall. So let's click solve, and as expected we saw this part fall off. Good. So at this point here, what we're going to do is also dictate some rotational motion on this part here. What we would expect to see is for it to rotate anti-clockwise, and this knuckle here will be in contact with this part. And that's what drives this wheel, this Geneva wheel, to rotate the other way also. So at this point here, what we'll do is specify some motion, some motors. Motors are different actuators in that motors would implement a rotational motion. So what we can do is also connect up this part to the slider. Now I can select on the center here and specify that the motor is going to act at the center of this surface too. And at this point what we will see is a motor that dictates the relative motion between them. We can specify the different type of motors that you might want to use. And for graphics purposes, it is really large currently, but that's just due to the graphic details that you apply it to, so don't worry about the size. At this point here, what we're going to do is just specify the motion. Currently it's got a step profile, let's make it a step dwell step. We'll have it step on duration for half a second, dwell time for 2 seconds, and step off duration for half a second. Now if this doesn't make any sense to you, what's nice is that in these little micro dialog boxes is that it gives you all of the properties around each motor. We can implement motor motion in the form of an angle, speed, acceleration, or torque. We'll keep it to speed for now. And if you click on this table function, you also see your profile editor. So this is what we mean by a step dwell step function. It steps up, it dwells for a little, and then it steps down again. So we keep it as this. End time will be 5, we don't need our animation to run on for too long. And our output rate, let's increase up to 50 Hz. So at this point what we will see is that we'll see this part spinning. Let me hide off this instead. So the shortcut keys to either isolate a component or to hide a component, you can just simply click on it and type in the letter H on your keyboard. Now at this point here we're going to add in an actuator motion, so we're going to specify a displacement of this slider where it will move across to this way after a few seconds of motion. So keep it on connected parts, click tick, and we should see an arrow point upwards. From here we can specify that we want it to move, let's say 12 mil, and we can give it the function of step only because we just want it to move off, and we can tell it to move off after 2 seconds, or maybe let's say 2.5. Okay, so once we've done all this we can leave everything as default. It's just a really simple tutorial to show you exactly how you can start simulating the mechanisms between your different CAD parts. So once your actuators are done, we'll then specify some contacts. There will be a contact between this part itself and this outer part there, so let's create some contacts there. And last but not least, what we're also going to do is also implement contact between this part and that part too. So if I do contacts, let's click on this one, and part 2 can be this outer ring again, and do create contacts. Now once that's done, again just leave everything as default values. Impact is a great contact type for when we have contacts that come in and out of contacts. And after this is all done, just click Analyze Motion. Like we said before, we keep the end time to 5 seconds, output rate of 50 Hz. It basically calculates how much data you want for every second. Now before I proceed, what I'm actually going to change is my motor. So let me just delete that off and try it again. Because what I do really want to do is to have my motor showing and not covering most of my CAD so that you guys can get a better understanding of it. So what I'm going to do is recreate it again. Let me hover onto this center, and there is an intelligent feature recognition tool in Inspire in that it recognizes when you've reached the middle of a line, or let's say the end of a line, the center of a surface, or the middle of the surface as well. So from here, I just want the center of this surface, and I'll connect up to this surface too. And with this center, what we wanted to do is same again, make sure it's a step dwell step function. So we'll have it 0.5, let's make this one 2, and the step off duration will be half a second again. And once we're done with this, let's solve for it. There we go. Now you can see that my slider has started to move before I've actually been able to wind up my wheel as much as I wanted to. So what we can do is go into my actuator here, and we're going to go back into the property editor and change it so that after 2.5 seconds of it, I want it to step off within half a second. Now you'll know that you have the options for your animation to start while solving or when finished. I like to do it while solving, so if I go wrong I can see how wrong I go very quickly, but if you do set it so that it animates when it's finished, it does solve faster. So I'm going to keep it as that for now, and I'm going to click run. And from here we can see it spinning. It's winding up our gear. So initially we did put just a pin in the middle there, so that you see that there is no sort of wind up, but it has stepped off properly. So at this point what we can do is actually put a coil spring. Let's put a torsional spring in the middle of this part here. So let's hide off this part. And what I can do is click on a torsional spring. We can apply it to the center of this face here. We'll leave all of the values as default for now. But now what we will find is that every time our gear turns a little, then there's a lot more potential energy, so that at the moment it's released, it should spin quite quickly. So let's solve it again. And this time after the second revolution, leads into our third, before finally our actuator will allow it to slide off, and you can see all of the potential energy that's released in that part for it to spin so quickly. Okay, so once we have all of that, we'll then obviously have an animation that dictates the whole motion for us. If you click on any of your parts, it will show you the part displacement, velocity, or acceleration that it undergoes in its motion. If you were to click on, let's say, the motor, it can show you the torque required to power the motion that you need. Or you can look at the speed. So if you're looking at any sort of control systems, you can look at the desired speed versus the actual speed. You can also look at the joint force that's exerted from that motor being there. We can also look at the actuator, the force required to power that movement again. In any of the joints that you have, so I can look at this translational joint, you can look at the forces that occur between the two parts when moving. And the same again in the pin, how much is required to keep the two parts kept together. Okay, now if you head into this run icon, this run button here, you'll see it's a drop down menu. I can click on it and look for the Force Explorer. And with the Force Explorer, it shows you all of the magnitudes of your forces, your torques, in your joints, in your contacts, in your motors, and in any springs that you have throughout the whole time in motion. And if it all gets a little bit confusing, we can always deselect certain values to focus on the ones we care about. So it could be that we only wanted to look at the contact forces. And you can see it work this way. Now once you've conducted any sort of multi-body dynamic analysis, what's really nice is that if you were to click on that part, right click, you can do an analyze part. This will then give you the options in that Inspire will mesh it for you. You can specify what loads you want to use from the motion for the animation, for the structural analysis that you want at the end. And I'll just specify to use all 349 time samples. And then all you need to do is click Run. Now, I've already ran mine, so all I need to do is bring mine back on screen, and you can see how you can then yet again play the motion, and you can see all of the contours that occur throughout its time in motion. So you can understand the stress values that it undergoes whilst it's being used. And this gives you a really good understanding in that should you then conduct an optimization, you know exactly which areas of material you should keep and which areas of material you should get rid of to make it lighter but performing still as efficiently as before. Now you'll see that, say if I were to click on a part, how we analyze this part here, you'll see optimize has been grayed out. Now in order to make sure in that you can optimize it, all you need to do is specify in Inspire that is a design space, and what it means when you specify something as a design space is that the moment you then have loads acting upon it, you can then actually have the option to optimize the part. Same options again. It will take you through a topology optimization or maybe a topography one. You can specify the percentage of the total design space volume you want it to use at the end, and any sort of manufacturing constraints can also be implemented from the structural toolbar. So you can specify any shape controls, any symmetric constraints as well, just to ensure that anything that you do create can actually be manufacturable as well. And this is Inspire in a nutshell. Thank you. Okay, so hopefully everyone can see my screen again.
Yeah.
Perfect. So just as a recap, why is that we should probably use Inspire Motion when conducting our designs? Now, with Inspire Motion, like we said, once you get all of your CAD in there, you can see how your mechanisms will move, so you can visualize the kinematic and dynamic analysis behind your parts. It gives you a really good understanding, so it knows what your component loads are and how it is that they interact with each other. Do you need to compensate it by changing the size of something, or do you need to change the motion? That's where you get the understanding from. You can take it through straight into an optimization where you can improve your component behavior given its motion. So not only in your classic sort of traditional, you can optimize based upon its structural performance. With MBD, you can optimize it based upon its kinematic performance. So say if you wanted to optimize it so that it would spin faster, then that's how you can change your different design in that respect. It helps you save time and costs. So where you can get your results quickly and you can derive your different load cases for your different finite element studies, it means you don't need to take it through physical testing. As long as you have all the right sort of spring parameters and the different motion kinematics behind it, it can save you that time and cost from having to experiment around to see what performance you need given your CAD parts. And just so you know, you can integrate it with other software. So you can easily share that functional model between software and your design teams. With Inspire, you can take that straight into our fully advanced MBD solver and motion view as well, where you can start incorporating in flex bodies, and you can bring in other nonlinear finite elements into that as well. But then you can also take your MBD analysis and send it straight to your structural team to conduct a structural analysis. Now, as we mentioned motion view previously, this is where we have the fully advanced multi-body dynamics with it. So Inspire Motion is great if you want a good, quick understanding of your parts. However, it is limited to looking at rigid bodies only. Whereas if you were to go into motion view, there is a vehicle library wizard in there. So if you wanted to simulate your full vehicle and do a double lane change, you can. You can tell it to follow a guided path. And like we said, you can also bring in flex bodies. So if you're expecting your parts to deform throughout its time in motion, then that's when we want to use motion view. Like we're talking about the vehicle library wizard, you can, you're not just limited to looking at cars. You can also look at two-wheelers and three-wheelers as well. You can look at them for your vehicle dynamics and control. So if you wanted to look at your rider-machine interactions, your vehicle stability when cornering and control, and any sort of driver and passenger safety, you can focus into that. You can also start looking at the durability as well. So if you're driving over pave, or if it's an unsteady surface, you can look at the component loads, the component fatigue life, and any damage that occurs. You can also start looking at the ride and comfort of your vehicles. So where you have the vehicle response to road, your rider response to the road as well. You can also bring in any sort of active systems behavior. So like we mentioned before, all of these models, you can link it up to Activate. That is the equivalent of Simulink. So where you have your 1D model, you can link up to your 3D model, and you can simulate interchangeably between them. So with the benefits of Inspire Motion, you can see from all these examples here, you're not just limited to looking at purely, gears. You can simulate it to understand how much force is required to pick a part up. You can look at an assembly, conveyor belt mechanism. You can look at simulating a washing machine, but you can also start looking at your excavators and what happens once you optimize them as well. So like we said, with a simulation-driven design, it gives you a full comprehension of your designs. It's quick and efficient. It uses motion solve, so this is our full capability and accurate MBD solver. So it's just a different GUI to motion view, but in motion view you can look at more advanced aspects of multibody dynamics. However, both of them use the motion solve solver in the background. It can easily take it through to motion view for more complex MBD analysis. So if you started off in Inspire Motion, it is a database that you can export out of Inspire Motion and open in motion view instead. And of course, you can start doing optimizations that are derived from your multi-body dynamic analysis. So thank you very much for listening to this part of the webinar. I will take any questions that you guys have. Feel free to write into the chat. So let's see what we have here. I know from earlier questions as well, some people asked, can we do a crash analysis with this software? You can do a crash analysis using Radios if you're expecting to see failure, but within Inspire Motion itself, it's purely looking at your mechanisms and the interaction between your different multibody mechanisms.
Yeah. I mean, let me read out two questions related to the MBD part. So there was, is it possible to analyze temperature during a multi-body dynamic simulation?
No, it's not. Any sort of temperature structural analysis, you need to use OptiStruct for it, or you can use AccuSolve for highly transient thermal analysis.
Okay. Then can we simplify symmetric features of complex model by, let's say, we use 1/4 of the Geneva wheel for simulation and then interpolate the results on the whole model? Are those results acquired that way viable?
You can, so you can simplify it, although I wouldn't say you needed to, because in multi-body dynamics, you would use your whole, your fully comprehensive CAD. You don't need to simplify it down because it won't really reduce any of your solving times. And you kind of want to understand, the whole motion of the whole gear. It could be that it works fine for the first half of it, but something in your motion might ruin the second half of the gear performance. So always use your full model. If you want to take it through for a structural analysis and you're assuming that it's going to be symmetrical, then fine. Yeah, you can simplify it that way.
Okay, so many more questions coming in. Can we simulate stress analysis of flexible bodies using contacts?
So when you want to incorporate your flex bodies, then that will give you the stresses and strains that your part will go through during its time in motion. And you can also use contacts on it. There are macros in motion view whereby you can make sure that you can put your flex body in contact with other bodies too.
Then there's does it use the same motion solver at the background?
Yes, it does.
Yeah, so that was a short answer. And then we have, is there a way to include the deformation caused by a rise in temperature through, for example, friction in the MBD? I think you answered that already. But we can't.
We're in multibody dynamics, in inspire motion, we're assuming everything is rigid, so nothing is going to deform. If you want to start looking at deformation that's caused by a rise in temperature through friction, that's something you might want to do using OptiStruct in a nonlinear transient analysis.
Okay, then we have, can you, for example, create a space frame chassis around a circuit? So can you create a variable path following speeds, frequencies to simulate an autocross lap?
Yes, you can. So in Motion View, there's lots of events that are already set up for you. You can edit them to whatever path you want it to follow. So really, you could take a car and make it do donuts if you really wanted to, but it's all in the software. You can just change easily.
All right. This next question was a bit the same. Let's say I run a double lane change test with my MBD model. Can I get the stress on individual components during that maneuver? If so, how?
Yes. So with the individual components, you just need to turn them, instead of being a rigid body, you want them to be a flex body, and you'll see the stresses it goes throughout its time in motion.
Yeah, exactly. So you can, for example, use the shown vehicle library, define your flexible components, and then define the task like a double lane change or a maneuver like that.
Yes, exactly. Yeah.
Then does it account for friction in the simulation?
It can. So in all your joint definitions, contact definitions, you can bring in friction, and obviously that will slow down your motion if there's any opposing forces.
All right. And then there are a couple of questions which are probably not related. They're related to radios and others again, so we'll answer those in the chat. Is meshing involved? Not sure if that is about MBD, but maybe you can answer that, Joyce.
So in the MBD side, there is a rigid body mesh that's automatically assigned to your CAD parts in the background, so you don't need to worry about meshing. When you're looking at flex bodies, you can either mesh your part yourself to get the proper stress results from those flex bodies, or in Inspire, it can do the meshing for you in the background once you want to look into a structural analysis.
Okay. And then there's one question about tires. Can we simulate tires while cornering and loading, and the tire temperatures and adjustable pressure and type of gas?
That's quite a detailed simulation.
Yeah.
So within Motion View, you are given some tire models that you can use, and from those tire models, it will show you the camber effect on them, the slip on them. But if you want to start looking at temperature effects and adjustable pressures, and the type of gas, that's something you'll probably have to go into OptiStruct to look for, because you want to involve temperatures. So it takes it out of the MBD region.
All right. Okay. I think that's it. We'll answer the other questions in the chat, as there are so many of them, and some of them are not related to the presentation. So I think we can go then to the final presentation and demo, again, by Joyce, which is Altair SimSolid now for structural simulation. So SimSolid is a program to do concept evaluations and rapid simulations using a new technique, which is related to finite element simulation, but not exactly the same. So this is used basically to do large problem setups of large CAD files, like you have here, a stage, a rotating stage of an opera located in China. And the whole stage, if you want to do it with traditional finite elements, is very hard to model and to mesh and to simulate. And there SimSolid comes into play. And Joyce will go ahead and explain you what is behind this, how to use it, and demo it on a welded frame. So again, let me make you the presenter, Joyce, and go ahead from here.
Okay, right. Okay, so hopefully everyone can see my screen.
Yes.
Perfect. So I'm going to be taking you through SimSolid in this part of the webinar. Now, for those of you who haven't used it before, or for those of you who have, same again as the last session that I did, we're going to go through the capabilities and benefits of using SimSolid. You'll then see a demo of the software, and obviously we'll address any question and answers at the end that you might have. Again, SimSolid is part of our simulation-driven design suite. So with your traditional FE processes where you have your part, you then need to defeature it. You need to make sure that you have good CAD. You would clean the CAD up, and then you would then probably, go through quite a labor-intensive method of meshing everything up. Now, with SimSolid, it basically uses a new technology that operates on your original unsimplified CAD geometry directly, and it doesn't need you to create a mesh. And you get your results within seconds to minutes. So if we're going to compare between the traditional FE process, that'll be the top bar at the top here, where a lot of time is invested into the pre-processing of it. I'm sure you guys have gone through, the pains of you bring CAD in, it might not always be perfect, so then you're sat there cleaning the CAD up, you're making sure that all of your surfaces are connected properly, and then after you've done that, you then need to make sure that you give it a mesh that represents your geometry well enough, and that it's a good quality so that you won't get rubbish results. And then the solve itself will probably take a little while to run, and you'll probably need to fight with other of your colleagues to make sure you get a license or to make sure that you get to submit it on the HPC in time. But then after that, you then have time spent on the post-processing of it, so the analyzing, the understanding of the stresses, and the way in which your whole assembly works together. Now, with SimSolid, the biggest difference in it is that you don't need to do any of the meshing, and you don't need to tidy up the CAD either. You bring the CAD in, SimSolid will know exactly how to handle your geometry based upon the setup that you've given it. So where you start constraining it, where you apply your loads, it will understand exactly where it needs more refinement and where it needs less refinement on. The solve itself, because of its new technology and the type of elements it's meshed itself with in the background, what the solver does is that it applies a high order integration equations on your a high order differential equations on your different parts of your structure in order to be able to calculate the stresses and strains and displacements at those different parts of your CAD. So that's the technology behind it, and that's different to the traditional, force equals KU, the F equals KU sort of formula that we're looking at. But then the post-processing of once you actually have your SimSolid results, that's all the exact same as you would have done previously. So where you can then start recording videos, you can take pictures, and you can export all of these values out as a table. And what this means is that the moment you reduce the amount of time it requires to mesh or to clean your CAD, it's a quicker and shorter process. So this gives you a lot more opportunities to run numerous additional studies, and it gives you a significant impact in the early design phase. So yet again, reiterating what we're talking about in the whole simulation-driven design phenomenon. So the way in which it works, like we said, in the new technology, it's meshless, so you don't need to do any of the meshing itself. And on the original CAD geometry, what it will do is apply those high-order differential equations. It works in high capacity, so you're not limited to looking at just the one part. You can look at a large assembly of different complex parts as well. It is accurate, so just because it's quick does not mean it's dirty. It goes through a multi-pass adaptive process, and it uses these smart functions in order to adapt itself so that it's giving the right stress value that you need it to be. And just so you know, it is very fast in solving. You can look at the speed and the scalability of it, and you get your results in minutes. You also don't need any sort of special hardware investments into it. It will just work straight off the bat using laptops, so you don't need any sort of high performance computing in order to solve for it. Now, the way in which SimSolid works as well is that you can use it with an assembly of big, small, thick or thin parts. You're not just limited to looking at the one type of results. You have you may have small geometry features inside your CAD itself, and you can keep all of these different small geometry features like pinholes or small fillet radius. You can keep them all in. You don't need to take them out because they don't cause singularities in your results. In the event that you might not always have perfect CAD, where you have part gaps and overlaps, you can actually keep all of these in. SimSolid is very forgiving, and it'll be able to keep these parts in for you. And it won't affect your results either in terms of the stresses around these imperfect contact areas. You can also start looking at extreme geometric complexity. So if you want to bring in any lattice structures, any scanned data, you can also simulate your stress analysis using these kind of inputs. And where you might need to use odd face transitions or small splinter surfaces in the drawing of your CAD, this doesn't get affected in your results either. So you won't see lines of meshes around these focus areas, and you won't get singularities again. So the benefit of SimSolid is the fact that you get a fast pace of design. The required time to solution would be minutes instead of days. You can deal with high geometric complexity with it as well, and you can deal with large assembly sizes. And all it requires is just 3 simple steps to get to that endpoint. In the modeling, when you bring your CAD geometry in, it will process your geometry, it will classify it as well, it will create the connections that you need for you, and it will also create your analysis parameters so you can specify exactly how it's being held, how it's being loaded. You also have the solving process where it will go through and it will then implement the mesh in the background for you. It uses a different type of element. And like we said, the higher order differential equations. And in the end, you have your results. So with the results itself, you can always get the same type of results from the analysis that you've implemented, whether if you're looking at displacement, stresses or strains, a modal analysis. You can also display the reaction forces and where it's being held. And you can always couple it up with a fast reanalysis. So if you wanted to change a small parameter, you can, and it will solve very quickly. And there's also an efficient coupled analysis. If you wanted to couple up your structural to a thermal analysis inside of SimSolid, you can. Now, these are just some of the known features in SimSolid that we're looking at. So like we said, you can look at statics as well as dynamics in SimSolid. Now, you can look at a modal analysis, and after the modal analysis, obviously you can take it through for a frequency response or random response as well. But then if you want to look at a structural, you have your linear and the non-linear side. You can look at thermal and any other sort of non-linear phenomenons like inertial relief or bolt pretension. You can include all of those in. And last but not least, you can also start looking into fatigue as well in SimSolid. Now, the types of materials that you can work with is the fact that obviously it can deal with your isotropic metals, plastics. You can also start looking at elastoplastic too. So where you want to start looking at bringing in the non-linear curves of your materials, you can bring all of that in. You can make different parts rigid. So if you know that they'll never deform, you can keep it as rigid. And one of the newer aspects is the fact that you can bring in orthotropic materials if you want composites. And you can also start looking at fatigue with the right stress strain and strain life curves as well. In the connections that you want, obviously in my tutorial later on, I'll be showing you how you can weld a frame together very quickly with the connections tool in SimSolid. But just know that you do always have the option to do auto connections. And from that auto connections, it will give you bonded, sliding or separating with friction. You can start looking at bolts, where you might want to incorporate bolts into them, any sort of pretensioning in them. You can bring in spot welds and seam welds and any sort of virtual connectors. If you want to do a remote connection type, you can. You can incorporate adhesives and joints as well. Now, last but not least, in terms of the results, like we said, if you're conducting a, let's say, a modal analysis in this aspect, what you will find is that you always get the same set of results from it. So you always get your frequencies and mode shapes, and you always get the modal participation factors from it. Say if I wanted to look at a linear static analysis, from there I'll always get my displacements and strains and stresses, and I can always get them in the form of XY plots. I'll get my forces in my bolts, and obviously you can look at everything in terms of a contour and animation. And the post-processing side, you can look at the minimum and maximum labels, safety factors, and bookmarks. So just so you know, in terms of the forces, such as your contact forces or the forces that are going through your bolts, you can always get these in a form of a table. So if you want to export it, and if you want to, post-process it in Excel, you can. Now here's just a few of the customer stories we have. Like we said, SimSolid is this, we call it new technology, but to be fair, it's been around for many, many years. And, loads of our clients are using it. It's accurate, it correlates to the physical tests, it works, and it's fast. So at this point, we're going to play the video. And after the video, I'll address the questions that you guys are writing up. Hello again. So I'll be taking you through looking at SimSolid and showing you exactly how you can get your results within seconds of importing your CAD into the software and understanding exactly how it's performing immediately. So at the end of this video, I'm hopefully going to be able to show you how you can take or bring in your own CAD, bring in your own frame structures, implement some connections on it, such as welds, and then you can assign a load case to it to then understand exactly how it's performing. Now for those of you who never heard of SimSolid before, I have done a previous video of this. It is on YouTube, and one of the main differences in that video is that it goes through a lot of your different user control options and how it is that you can directly implement your new sort of CAD designs. And what it does is that SimSolid will then take your original design study, creates a new design study for you with all of your load cases mapped over so that you don't need to go through that process again. So it's great for looking at quick CAD iterations, whether if your CAD changes have improved your design or not, whether if your different CAD iterations have improved your designed parts, and you can see exactly the stress levels around each of the parts itself and displacements. And SimSolid does all of this for you seamlessly and in an incredibly user-friendly manner. So let's not dwell. I'm going to show you exactly how you can bring your CAD in, and you can then set it up for a load case like this, implement some welds that you see that you can generate for your different parts, get some stresses in those parts as well, and understand how it's performing. So you'll see that at the moment we click on the play button, we can see the way in which it deforms, its deformable shapes, and the manner in which it's being used in. So let me close off this session. Now, within SimSolid, again, it is CAD agnostic like all of our other softwares, meaning you can bring in any sort of CAD format you need. You don't need to put it in a specific file format. It can read in everything, including the native CAD formats from your different CAD packages. So what we'll do is at the moment we bring this in, we'll see that it creates a new design study, and within that design study itself you can see the assembly associated to each of these. So the assembly of your different parts. Currently it doesn't have any connections at all, and it's got one structural analysis assigned to it, but I can delete that for now. So let's start off with just the basic CAD. Now in the assembly itself we can look at applying a material to it, because obviously with all our parts we need to assign a stiffness value in order to be able to calculate a finite element analysis on it. So within SimSolid what we're going to do is let's just assign steel to all parts, close, and once you see that that steel has been assigned, you'll see that a material will be assigned to the end of these different part names, so you know exactly what material everything is. Now if you're working with a huge assembly of parts, you can always check for unassigned materials by simply clicking on, or unassigned parts by simply clicking on show, right click on assembly, show parts without materials, and if everything has been assigned properly then it will tell you that there are no parts without material assigned. Now the workflow we also recommend is that if you know you have an amalgamation between welded parts as well as bonded contacts or connections that you want to implement in, we always recommend doing your welded contacts first. So within SimSolid you can create spot welds or seam welds or adhesives, just so you know that you do have lots of different virtual connectors that you can also use. Now say if I wanted to create new seam welds, You would specify your section size and the minimum length in where it is that you want to implement a weld upon, and there's so many different ways in which you can do it. For now, I'll just do a group weld, and what I will do is hold down Shift to do a box select of my different parts. Sorry, hold down Control, do a box select of all my parts, and then at this point what we're going to do is click on Find Welds, and you see very quickly it would have found lots of different welds. Total number is 212, but what you can then do is then zoom in and see exactly where all these welds have been placed in your structure. And whichever one is highlighted, so say if I highlight number 17, we don't know where it is in this big assembly, just click on this magnification icon and it'll show you exactly where weld 17 is. Once we're happy with that, click on OK, and you'll see very quickly SimSolid's already done all of your seam welds for you. Now at this point here, we can also use this button. You'll see that where you click in your project tree browser, if you click on Assembly, you have the Assembly Workbench toolbar. If we click on Connections, we then get the Connections Workbench toolbar as well. So just so you know, with this button here, if you click on it, it will show you if you have any disconnected group of parts, and what it should tell you is that you have no disconnected group of parts at this moment. Great. So once we've done this, what I also want to show you is that this main top toolbar up here, within my other video on YouTube, it will go through all of your different user options that you can go through, the way in which you want your CAD to be displayed, how to hide parts and show different parts, and your different selection tools. But what I will focus upon in this video is the fact that with this end set of buttons would be the different types of analysis that you can conduct. Within SimSolid 2021, we can start looking at structural linear, non-linear. We've always been able to do this. We can specify to look at a modal analysis, dynamic analysis, so whether if it's a transient analysis, frequency response or random response. You can also conduct some thermal analysis as well, but within 2021 you can also look at fatigue, whether if it's stress life or strain life, whether if you want to check for the life cycles that your part can endure, or just the damage that it undergoes. You can conduct fatigue within SimSolid. But for this tutorial, just this example, I'm going to conduct a structural linear for now. And within structural 1, the moment you set up a load case, you'll see you have your load case workbench toolbar. And at this point, if you click on immovable, I'm just going to specify that I want all of my bottom faces to be constrained in all degrees of freedom. Now as you go through and click these different faces, if it's easier for you, you can click to have your edges showing, so that's easier to see. If it gets to the point where you don't remember which faces you've selected, you can always do a shift select to see if you've missed any out, and you'll see that I've missed out this corner and this corner. So now if I do another shift select, we can now see that I've highlighted all of my bottom faces properly. So I'll click OK. You can see my constraints are there with these yellow crosses. For the next part, I then want to implement, let's say, a force to act on the top surface of my frame. Same again, we can go through and let's say if we do add tangent faces, if I click on this one face, you'll see that it'll apply to everything around it. So if that is something that you want to do in, let's say, your frame or a chassis that you're looking at, then that is an option that you can tick without having to go through everything. But it's not what I want to do for today, so what I'm going to do is just go and click through each of these individually. And same again, I can go through and click on these different top faces. Now you also see that within SimSolid is that you don't have the option to edit your CAD or your geometry the moment you bring it in. So what I did want to make you aware of is the fact that you can use spots. So say if it wasn't the whole surface you want to apply the force to, but instead just a tiny square surface on this area. Now what you will be able to find is that with spots you can specify exactly the area in which you want to implement spots upon to actually apply your load cases to. So just so you know, that is another option that you can use. And now let me do a shift select to make sure I've got all of the top faces that I needed. Once that's correct, what we're going to do now is head over to looking at our global axis. We want to have a downwards force in y, so that would be negative, and let's specify negative 10,000 newtons. And once we're okay with this, just click OK. We'll see some pink arrows showing up, and we can solve for it this way. Now if I click on, just so you know, you do have other loading options as well. We won't be touching upon it, but you can use enforced displacement. So if you're trying to replicate real test data and you don't have the forces behind it, you can use an enforced displacement to emulate that distance traveled. We can apply inertia loads, gravity loads, so any G loads that you want, any inertia relief. You can do remote loads, bearing loads, hydrostatic pressures, etc. So if I were to click Run right now, you'll see the bottom left corner is where your software is talking to you and telling you exactly what it's going through in the solving phases. And within seconds of clicking Solve, you already have your results. So if I now look at my von Mises stresses, I can click for play, and we can see exactly how it's displacing by and where our maximum stresses would be. We can click on the min-max values, and you can see that the maximum stress occurring right now is actually at the back part here, acting upon a weld in itself. And say if you wanted to, dramatize your contour plots, you can always adjust these accordingly. So let's make this 5, and let's make this one 0. So you can see which areas undergo most stresses. And let me reduce this down a little bit. I realize that my loading is quite low compared to the rest of the strength of this frame. And you can see anything that exceeds over, let's say 1 in this instance, we can see exactly which areas are most stressed. You have your usual options at the side here where we can increase the oscillation of your animations, how continuous and discrete your animation is as well. So if you want it to look more robotic, then obviously it'll be less continuous, and the more continuous it is, the smoother it looks. It could be that you wanted to hide off all of your contacts. So say if I go into connections, we can hide off our seam welds. So if I do hide all, and now if I go back to displaying the results of stresses, we can see that the maximum stress on the actual beams of our assembly is only around 1.3 megapascals. Now at this point here, like we said before, if you do any CAD changes, just simply do project and import from file, bring in your new CAD iterations, and everything will be mapped over for you. You can watch my previous video to see how you would do that. But with this one again, what we can always do is if you simply right click copy, you'll see it paste that structural 1 load case into a structural 2 load case, and you can easily vary it to see exactly how high you can load it up before it starts yielding. So I can do that in this way. I can also then again, let's do another copy and paste. I can then change it so that instead of this value, I can put it so that it acts in the X, Y, or Z value, however you want to set up your different load cases. But I can delete that one off and simply just add in a modal analysis as well. And within this modal analysis, again, we can copy and paste it. But what's nice is that, let's say if I take this immovable constraint, I can copy it to a certain load case as well. So I don't have to copy and paste whole load cases. I can take one aspect, such as that constraints there, so that I have one free modal analysis and one fixed free modal analysis. And once that's all done, I can simply just click on the whole design study, and I wanted to solve for everything. And you'll see whichever one's highlighted in bold is the one that it's solving right now. And within a couple of seconds, throughout every time it solves, you can see how quickly it goes through and gives you the results that it needs. So every time you have a set of load cases with results, a new icon would show up saying result, and you'll have the results that you need for each of them. Now, just because it's fast is by no means is SimSolid an inaccurate or dirty solver. We've done plenty of internal benchmarks to validate its results, and you can visit NAFEMS online or access the NAFEMS article to look at a benchmark that they did between SimSolid and all of the fully advanced, traditional FEA solvers as well. And last but not least, it's now finally solving the fixed free analysis. And once all of these are done, you can go through and click on the results to analyze them and understand exactly how your parts are performing. Okay, so once this is done, we have these results here. So if I go through and just go through each of these results, now we can see, let's look at displacements. Now you'll see there's also live synchronization between the window screen, and say if I was to click on structural 2 immediately, it will show you the same type of displacement contour plot, but for the different structural load case. So very quickly you can flick between the two to see the differences between them in results. And obviously, as we expected, the loading in structural 2 is 100 times greater, hence you can see that in the results as well. And say if we then went through and clicked on the stresses, same again, because we've hidden off all of our welds, we can see now the maximum force, the maximum stresses occur in the same location. With the modal analysis, like we can see here, the first 6 ones in our free analysis would be our rigid body modes, so how it would displace and rotate in degrees of freedom X, Y, and Z. And then when we go through to start looking at its actual natural frequencies, you can see whether if you have your bending modes or if you have any torsional modes instead. And same again for the modal 2, because we actually constrained it as now a fixed free analysis. We no longer have your first 6 rigid body modes, but instead you get to see the natural frequencies, whether if they're bending or whether if they're torsional modes. And say if you wanted to conduct this whole analysis again, but changing the material of the part you're using, you can do it very simply by just simply right-clicking on Design Study 1, copying it, and you can see it's copied everything over into Design Study 2. But what you could change very quickly is just Assembly, and let's assign aluminium to all parts. And you'll see once we have all of these aluminium parts here, we can tell it to solve for it again. And these can be the different design iterations that you might want to look into. And last but not least, I'm just going to show you the quick processing of this as well. When you have a moving animation, just click on the camera icon, and because it's moving, it knows to save it automatically as a video. Let's say we're actually looking at, let's make this a bit more dramatic in terms of the scale deformation, and let's say this is the angle that we care about. It's no longer a moving animation. If I take a snapshot, it knows to save it as a still picture format. So very quickly you can right click and save media to files, and then it exports it all out in the correct format you need for you to put it into reports, PowerPoints, your Word documents for quick reporting. And this is pretty much how you can use SimSolid for rapid structural analysis in any of your different design processes that you might want to use. Thank you for listening. Okay, so hopefully everyone had a really good understanding in how it is that they can incorporate SimSolid into their workflows, the benefits of it, and just the speed at which you can get results from it. So what I'm going to say is that with SimSolid, the recommendations around it is the fact that you want to import only your solids, don't bring surfaces in, and make sure that your solids are properly closed, so no open solids with it. And just make sure that you keep it to your high fidelity CAD models. You don't need to worry about defeaturing it or anything. Just keep it as it is. And just so you know, you can work with CAD as well as STL, so any scan data that you have, but just be careful because obviously with scan data, it will assume all of it as one surface. So just make sure if you can bring CAD in, just bring your CAD in if you can. Use your CAD geometry as is. So where you have pinholes and everything, don't feel like you have to remove them. And where you're actually working with large assemblies, that is completely fine. Don't worry about having to simplify it down by merging them together or assuming that they're one part and specifying like a boolean between your parts. You don't need to do any of that. Just bring your large assemblies in as they are. So in conclusion, obviously we know for a fact that SimSolid isn't just tied down to the one sector either, like with all of our products. You can look at them from a construction form or from a biomedical form. Now, it is super game changing in how rapid your design iterations can be if you were to use this. It gives you a seamless workflow, and it's got a very easy to use GUI as well for you to interact with. It's very user intuitive. It also eliminates any sort of geometry simplification and meshing that you might need to do. So if you just need a quick result, just use SimSolid. It helps you analyze complex and large assemblies. So you're not just limited to looking at the one part, you can bring in thousands of parts in, like the example that Jan showed earlier, that stage, that elevating stage, that's got more than thousands of parts inside of it, and it solves super quickly. And like we said, just using a standard PC or a standard laptop, you can get your results in minutes too. And like we said before, there is a NAFEMS article on SimSolid. So before when we were developing SimSolid, we always make sure that we did our own internal benchmarks, and we did it heavily from comparing SimSolid to OptiStruct, which is our full-blown structural solver as well. But then external parties like NAFEMS, if you haven't heard of them, NAFEMS are like a governing body of looking at finite element analysis as well as all simulations to make sure that the tools that the engineers in the world can use are safe and reliable. And NAFEMS did a benchmark where they looked at comparing SimSolid against their fully advanced CAE solvers as well, and you can see that the discrepancy in the results is less than 1% for most of them. The biggest difference is only 4.2%. So if you do want to look at the article, do let us know. We can upload it here again as well for you. But thank you very much for listening. I'll take any questions that you have now.
Okay,
so let's start.
Thank you, Zoris. Yeah.
No worries.
I already uploaded the NAFEMS and the technical white paper to the handout section. So if you want to download it from the go-to window handouts, you should be able to see the NAFEMS article and also a technical white paper about the technology behind it. Because that question was asked multiple times already in the chat, so I uploaded it now.
Perfect.
Yeah, exactly. So was one question: is it possible to use composite materials with a specified layered pattern in SimSolid?
To that detail, no. You'd have to use OptiStruct and HyperWorks. The only thing that you can use in SimSolid are orthotropic materials.
Yeah, I mean, I have seen an example of a skiing geometry where the model consisted of the CAD model consisted of multiple layers. So the CAD designer designed like 10 or 20 layers of material within the CAD file, and then you could use it, but that's usually not possible or feasible for composite design. So the answer is usually no, as I said, of course. Then are we able to specify the time for which the force is applied in SimSolid?
You can do a transient analysis where you can specify at which point you want the force to be applied on, so yes.
Then which type of CAD file format works best for importing? Do you have an experience there?
Well, so SimSolid is a CAD agnostic software, meaning it can read in any CAD file format, even native ones like TFV5. I always go by Step or Parasolid. They work quite well for me, but they're just the ones that I have available.
Okay, then there are two questions which are quite related. So what are the drawbacks of SimSolid, and are there use cases where manually meshing the structure is superior to SimSolid?
So the drawbacks of SimSolid is it is just limited to analysis. So if you want to take it further for an optimization, it doesn't do any optimization in there for you. That's when you might want to use Inspire or HyperWorks instead. The other drawbacks are, I guess, if you want to look into high-level composite modeling, you can't do that in SimSolid yet. And are there cases where manually meshing the structure is superior to SimSolid? Again, I'd say if you want to take it through for an optimization, then yes, you might want to manually mesh it instead. Other than that, if you don't need to do an optimization, then SimSolid can do most of your analysis for you.
Yeah, I think it's mainly also when to use it. So I think SimSolid is very strong at an early design stage, and
Yes.
the more detailed your simulation results have to become. Like, let's say, for example, if you want to simulate the whole welded structure, then SimSolid is the right tool. Now, if you're interested in like a single weld, so only looking at the detail of the weld and how the stresses and strains inside the material or in the volume will decrease or increase, at that level of detail, you should then again probably use a meshed model of a like a cutout of the whole geometry. And yeah, the advantages of SimSolid is the larger your structure is, the faster basically it is compared to classical meshing.
Yes, you're absolutely right.
And
yeah.
the more detail you need, then you should probably go to classic meshing.
Yeah, and if you wanted to do like simultaneous analysis as well, so if you wanted to weld one side first and then you want to weld another side, this sort of sequential analysis, it's probably something you want to do in OptiStructure because you can't do that in SimSolid.
Yeah. The next question is also a bit related. How different will be the results as compared to the traditional solver? So how is the mesh convergence determined?
Okay, so we've already addressed how different will the results be compared to traditional solvers. It's basically the NAFEMS article, as well as if you want to give that a read, then the biggest discrepancy is probably around 1%. In terms of the mesh convergence study, instead of determining the mesh size that you need, you would just need to specify the refinement levels that you need in SimSolid. So how many further iterations it needs to solve for to get you to your converged result.
Yeah. Okay. Does environmental effect like rain, wind, etc. can be simulated using SimSolid or Inspire?
You can specify a transient temperature in all of the cases, but in terms of rain and wind, etc., you might want to start using probably FSI interaction, so fluid structure interaction for that. Although I'd say in any sort of simulation world, unless you're looking at agricultural, that's a bit of an overkill. You just need to make a few assumptions for most of your simulations, yeah.
Okay, and then about SimSolid, let's say we import an assembly from SolidWorks or CATIA, just fixed in space parts won't work, so each and every component has to have key constraint or mate features? Question. Not sure if I get that.
Let me try and... so if I understood that correctly, if you're importing a whole assembly, just fixed in space parts won't work.
What I understand in the way, do we need to define additional constraints on each component? But I would say no. We can just import and start calculating, because upon import, all the different parts will be connected automatically by SimSolid.
Yeah, pretty much. Yes.
So there's an auto contact feature on importing. You can define an automatic tolerance.
Yeah, like Jan said, there's an auto contact feature, so you don't need to worry about having to do constraints for individual ones.
Okay. Then one question which came up multiple times was, is it included in the free student version? So can you use SimSolid in the free student version? Yes and no. So there is SimSolid included in the student version, but it is accessible via the Altair Inspire interface. So you have to install Altair Inspire in the student version. You can then go to Preferences in Inspire and select SimSolid as your solver. For the version that Joyce showed in the demo, you would need a full license. You can get that either through sponsoring or through the campus, or you can request a 2-week trial on our website, usually going to altair1.com. There you can request a trial version for 2 weeks, and if that's interesting for you, you can then either contact our sponsoring or the academic research team in your country. Okay.
Okay. Any other final questions from anyone?
Will food be provided at the end of the session? We can fax it to you.
Yeah, just make sure you stick your head out the window.
Yeah.
Don't catch it with your mouth.
Exactly. Okay. So thank you, Joyce, again, for sharing your experience and showing these models and demos.
Not a problem. Thank you for having me.
I think we'll still stay online 5 more minutes or so and answer a couple of more questions that have been unanswered so far. And until then, I hope you enjoyed the webinar. Hope to see you tomorrow again. And then my colleague Laura and some other panelists will guide you through Altair Inspire and how to use Inspire for optimization and simulation. All right. Another topic tomorrow will be, I forgot about that, will be the software SimLab, which is used for multiphasic simulation and meshing of multiphasic problems. All right, so have a good day and enjoy the rest of your day wherever you are in the world, and hope to see you again tomorrow.